Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to today's webinar, Powering Resilient Energy Infrastructure. My name is Amanda and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them, their cultures and to elders past and present. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, SMEC. For 75 years, MEC and SJ Company has built a reputation as a trusted partner on major energy, transport and water projects around the world. At SMEC, they do not only plan for energy transition, drawing on a global network of specialists and a delivery record that includes over 33 gigawatts of solar, 3.6 gigawatts of wind, and 11 gigawatts of hydroelectric projects. They create integrated end-to-end systems in renewables, power, gas transmission and distribution, bioenergy, and decarbonisation across sectors. Today's session will feature our guest speaker, followed by our live audience Q&A, and I encourage you to send questions through to our speakers via the chat box. I'd now like to welcome our international speaker, Wu Liang Tan, Senior Executive Director of Global Energy at Sabana Jurong. Wu Liang is at the forefront of this transformation, leading SMEC and SJ's global energy portfolio. As the global lead, he is pivotal in empowering clients with the technical expertise and advanced engineering solutions to rapidly reduce carbon emissions and transition to net zero. Together with the global energy team, he is making a real impact, engineering positive outcomes with energy that is sustainable, affordable, and reliable for all. Please welcome Wu Liang Tan.
Thank you, Amanda. Good afternoon and evening, ladies and gentlemen, Engineers Australia community as well. My name is William Tan. I come from Sabana Jurong Group, and in Australia, we're better known as SMEC. I would like to express my deepest appreciation to Engineers Australia for extending this prestigious opportunity and for graciously hosting this session as well, allowing me to share on a very important and ever-evolving hot topic on energy infrastructure resilience. So without further ado, I will share the contents of my presentation today. Next slide, please. As a start, Sabana Jurong Group, we are a major international engineering practice, and this is a stat showing what we do around the world, as well as the number of people we have. With over 70 years of experience globally developing critical infrastructure, mission-critical infrastructure for both the public and private sectors, garnering close to more than 2.2 billion Singapore dollars of revenues on a year-on-year basis. So we've been delivering sustainable, affordable, and reliable energy for all. And we believe in real impact made together. Next slide. So this is the content of my presentation today. I will start off with a quick introduction about power infrastructure, then move on to talk about smart grids, energy storage system, distributed energy system, transmission and distribution, and then I'll end off with a quick note. Next slide. Now, this is what happened in April 28 this year. Spain's unprecedented power outage sparked a blackout blame game over green energy, and questions about reliability and resiliency of energy infrastructure came into play. For most people on the ground, it is a wake-up call and a quick signal on what energy infrastructure is and how critical it is to their daily life. But for the engineers, it basically put into question grid stability. How do we ensure power system have the right frequency and voltage and supply as well? So the outcome of an investigation, and I quote, was that grid was unable to cope with a surge in voltage that triggered a cascade of power plant disconnection, ultimately leading to the outage. But little also known is that besides Spain, Portugal also suffered the same fate. And to a certain extent, there was also a power export to France. And again, I quote, an atypical oscillation was detected, which resulted in a reduction in electricity export to France, which led to an increase in voltage. Now, what all this meant is that it came to questions a lot of things. Was it our renewables implementations that created this outcome, which authorities highlighted it may not be? Is it due to a more interconnected grid that created this outage as well? Again, all these questions come into play and make us start to think, how can we ensure grid resilience and grid reliability can be enhanced? Next slide. Despite these outages, the power sector is still slated to grow very strongly. And why? This arising from the need for decarbonization, the need for grid modernization, and a critical need for electrification. So these key drivers for power asset capex spends are coming from all these different reasons and drivers. So renewable energy, transmission line upgrades, aging grid also needs to be modernized and upgraded. With the introductions of more utility scale renewable energy, we also see the need for high voltage as well as extra high voltage transmission requirements and substations infrastructures. Electrification also is creating a greater demand and more pressure on the grid as well. And of course, industrial growth and other generation growth comes into play as well. So we will see potentially a year-on-year increase in capex spend on power asset of up to close to about 8%. Next slide. But then and again, we still face a lot of existential challenges. What are they? Climate change. Existential climate change still pose a challenge to our quest for reliable and resilient energy infrastructure. A lot of our infrastructures were built more than a decade ago, or even sometimes 2 decades ago, more mature economies. And during that time, design considerations, factors, safety factors that we put in place are different than now. So as engineers or power engineers today, we then need to look at how do we overcome those challenges such as climate change on existing power infrastructure. How do we then mitigate this and not repeat these kind of challenges again for the next generation? Next. Now, grid resilience is a very, very important aspect to think about. This basically culminates into our capability to withstand, to respond, as well as to recover from power disruption. The next thing is about reliability. We also need to then ensure consistent power delivery by minimizing any outages as much as possible. So, what then are some of the potential initiatives that will enable us to have a reliable and sustainable energy infrastructure? And today, I just like to share a few amongst many other possible solutions. The first I'll start with is smart grids. Next slide. As you can see, a lot of our power IoT can basically put into place to convert conventional power assets into smart grids. Basically, a lot of smart devices can now be connected from both the demand and supply side. When we look at the entire system today, we can look from generations, we can be able to do forecasting. We will be also able to look at automated control of power plants. And on the transmission and distribution end, we can use IoT to maintain grid stability and reliability, further strengthening the resiliencies of the grid. And on the consumption side, we can look at aggregating and controlling distributed energy resources, automating our demand side management, as well as operating connected mini grids and creating grids of grids, put it that way. Next slide. The decentralizations of grid will further help to strengthen the current grid infrastructure that we have in place. So on the renewable energy generation forecast, these are some of the things we can do. We can enable data access from remote DERS and grid stage, and we can also use real-time data to increase the forecast or the reliability of forecasting for renewable energy. Weather data today can also utilize AI technology to help us get more reliable and more resilient AI data coming out from weather. Automated control of power plant will allow us to look at prediction-based proactive operations, and we can also use sensor instruments on a lot of our equipment to detect in advance and predict any potential maintenance or fault that could potentially appear. And on grid stability and reliability, substation automations, intelligent comms network, fans, and two-tier architectures, aggregate and control of industrial and residential loads, which is high demand loads, will also be able to be dealt with. And of course, on the consumer side, as earlier mentioned, we can look from transitioning one-way power flow to two-way. Then this can be alerted as well on the power demand so that consumers, retailers, and service provider could react and benefit as we need to and reduce the state of what I mentioned earlier or what happened in Spain. Next slide, please. Blockchain technology are also creeping into the IoT space to look into how we can create smart grids. So they could potentially transform the power sector by using smart contracts and to look at optimizing and coordination among the different applications. So peer-to-peer power trade, grid management and system operations can then play a better part. And all these are in part helping to basically strengthen the overall grid system and infrastructure. So grid management and system operations, the automations of power trading based on real-time data and so on will create a different model for us moving forward. Next slide. This is an example of what we have done for one of the developments here in Singapore. The smart grid was part of a net zero roadmap for Health City. The Health City consists of various blocks of hospitals, healthcare units, even a very critical disease center, as well as also age well development. The demand and the load profile from the different buildings and the different clusters are basically very challenging. So we have to look at how then can we create the necessary power systems or generations sources to support it, with an intent to basically decentralize from grid power. So we look at potentially renewable energy resource can be generated on site. We look at energy storage systems that can be put in place, as well as even more innovative, but again, not commercially viable yet technologies that look at fuel cells and so on. And integrating all this into a smart distributed energy management resource system, a DERMS system. By doing so, we're able to then look into automation, optimizations, cybersecurity, energy trading, as well as even the asset health monitoring in respective modules, thus allowing an integrated smart grid to be configured on site and allowing cost savings as well as also real-time management of demand supply response. Next slide. The next topic is on energy storage system. Energy storage system is becoming more and more a very important component in all this development. Next slide. Now, despite that, what I said earlier, we still need to match the energy storage system technologies correctly to the right applications. These are all centered around the discharge rates, the power ratings, and the module sizes. There are various types of energy storage systems in play. And every country have a different needs. Some country provides, or some regions and context wise, provides the availability of maybe pump hydro energy storage. But if you look at Singapore, you can't have it. But in Australia, you can have it. Then you look at NMC batteries, lithium ion batteries, which are most common and most bankable. And you look at also potentially moving forward flow batteries using vanadium redox supercapacitors as well, and also fuel cells, and maybe even other mineral type of battery, including sodium and so forth. But each and every one have a different performance, and each and every one also have different economic commercial viability, and also different maintainability as well. Next slide, please. So if you look at the entire energy storage system, it couples with looking at examining the total cost of owning the LCOS as well, the benefits in terms of even looking at cost benefit analysis, and looking at the operability and maintainability of the battery life. There are many, many OEMs in the world. The cost of batteries, of course, for LFP and NMC batteries are being driven down in the current situation. So making energy storage even more viable at this point in time. But then we got to look at the overall cost throughout the life of the battery. There are various aspects that also need to be dealt with in detail before we choose the type of energy storage system that can couple well and most compatible with any generation sources that we are speaking about. Next slide, please. ESS obviously has a grid forming capability, and that's the reason why it couples very well and provides a solution for high renewable energy penetration. Where intermittency comes into play, energy storage system can play a very good role. So grid following microgrids are what we always have. The grid forming part of it, of microgrids, are what is the trend moving forward. So as a grid forming microgrid comes into play, we can basically establish the voltage and the frequency by ourselves. So you act as the host. You're not controlled by what is the existing grid modus operandi. Flow batteries are also becoming more and more popular. There's a lot of look into that because it's highly suitable for grid forming capabilities because of its long duration storage capability and its high cycle life and safety as well. However, we then need to look at the bankability of it as well. So based on some of our experience implementations of some of these batteries, commercial institutions still prefer more mature, more maintainable kind of technologies at this point. But we do see trends moving towards some of those other energy storage system that I mentioned. Next slide. This is an example of one of the projects that was done, whereby a first of its kind underground hybrid energy storage system is being conceptualized. So this is where we put LFP together with vanadium redox flow battery combinations together for an urban development. So this is done in collaboration with the OEM, the technology provider as well, to look at putting and pioneering the world's first underground hybrid system, energy storage system, to be accurate. Now, why is the need to do so? Is to look at, number one, solving a critical issue of space. Two, studying the safety and the risk factors concerning between flow batteries and lithium-ion batteries in confined space. With that knowledge, we then will be able to look at creating better legislations as well as standards to govern such implementation. There's also the need to look at getting regulators, and this is very important factor in many countries, is how to convince regulators that such developments can be put in place safely and risk averse of it. So this is another very important aspect to think about. You got to get regulators on board with us when we are implementing such technology. So we need to work has engineers very closely with OEMs and the regulators in a lot of contexts. Next slide. Distributed energy resource system as well does. Next slide. So those are gaining also a lot of momentum. You can see a lot of these examples that are quoted here. From hydro coupling with floating solar is becoming the norm today. A lot of hydro dams, reservoirs are now decked out with floating solar. Floating solar PV adds another dimensions of renewable energy generation on top of whatever the water body is used for. Solar with BESS is already a commonality, especially for a lot of utility scale projects. Hydrogen storage combined with fuel cells, onshore winds with BESS, biomass waste energy facilities, plus wave, tidal, plus solar hybrids, together with storage. And conventional CCGT power plants are also having add-ons of lithium-ion batteries for black start operations and grid forming facilities as well. Next slide. So here again, two examples. One is one of the largest uh, hydropower project currently undertaken in Malaysia, whereby we are both the engineers for the hydro dam as well as the floating PV. There's close to about 1 gigawatt peak potential for floating PV on the power dam, hydroelectric power dam. And this was designed in a modular basis to ensure that the modularization can allow the full potential of implementing FPV on the dam when it is dammed out. So we conducted a very extensive FPV study. Now, what is more challenging is not about decking the FPV on the dam. What is more challenging is the depth and the geological conditions underneath the dam. It's a big valley, deep, with more than 100 to 200 meters at some points of depth. So you can imagine, how do you anchor a FPV onto such great depths? So we have the expertise to basically design such anchoring system from our marine expertise. Another example is this, probably more familiar for those residing in Australia, or ASEAN, whereby we developed a solar grazing on a 520 megawatt AC Stubo solar farm that's coupled with BESS. So you have dual land use for it, where ships graze around the PV panel. At the same time, we basically are optimizing both land use and RE generations and storage at the same time. Next slide, please. The other very important one, we can generate all the electrons that we want, but can we bring the electrons to where it needs? So the transmission and distribution grids are the most crucial. Next. So these are some factors that challenges grid along the lines. Voltage stability, frequency stability, and of course, load flow management. To ensure that all these challenges are met, there are various approaches and technologies that we can put in place, as listed here. I won't go through every single one, but these are all aspects that we need to think about when we are designing the grid and designing for the future. Next slide. So as it is, when we do any grid planning, we need to be a bit strategic in thinking. It has to be able to enable better visibility of power transmission as well as the generation assets. And hence an integrated approach is what we believe will be the best way to do it. From grid modeling aspect, we look at forecasting, looking at macro supply and demand forecasting, to looking at weather forecasting. As earlier I alluded to, AI is now helping us to get much more reliable, and more real-time weather data. There's also asset failure forecasting, so more sensoring and put in place to allow us to look at predictive maintenance and to even predict earlier when do we need to do maintenance. All these put into a simulation layer will then evolve into a solution that we can then put in place depending on what the context of the grid stabilizations that is required. But last but not least, very importantly, is look at the economic and stability, viability as well. Now, what we need to recognize is that a lot of our grid infrastructure has been built for decades, and we are always running most of the time on the AC form. Now, this is the way that we have designed transformers. Our transformers or the OEMs has designed it to be, and we have to conform to that. So, with newer implementations of DC or even microgrids and the introductions of more RE, we have to conform to that. Otherwise, you can imagine utility operators and developers will then have to overhaul the entire grid, which is too costly. In recent report, I see we need up to even 2050 to invest trillions of dollars in order to upgrade our current grid to a HV or EHV grid modernizations program for the whole world. So this is a very, very long-standing challenge that is facing the world when we look at grid modernization. Next. With the need for grid modernization coming to play, you also see more trends in terms of looking at modular underground substations. Because of the challenge of land in certain spaces in big cities and the need to yet upgrade our grid to HV or EHV levels, we then need to see how do we coordinate this together. Hence, going underground might be one possible solution. So as an example, in Singapore, we have designed the first underground 230 kV substation, and at the moment, there's another project coming up very soon for 400 kV. This is for cities that is highly dense. We've got to look at alternatives. Long distance subsea HVDC cables are also gaining momentum. I think early stages in Australia, there was a project, Sun Cable, that was intending to send electrons generated in Northern Territories to Singapore. And that involves HVDC transmission. Not only in this part of the world, in Europe, there are also a lot of HVDC undertakings. Then this basically allows countries interregionally, transnationally to move electrons from point to point. Mesh and ring networks are also gaining momentum. Buried cables, not every country needs to undertake buried cables, but more and more because of safety as well as also the need to cut across urban communities, this has risen more and more. But cost-wise, it is still definitely more costly to do a buried cable as compared to overhead transmission. And of course, HVAC, HVDC uh, implementations, depending on distance and locality, is gaining more and more momentum, especially for cross-border and intercontinental. Next slide. Now, I've earlier have shown an example of how climate adaptations or climate risk could create a challenge to our power infrastructure. Climate adaptation is crucial because we need to be able to ensure that our power infrastructure can withstand such climate risk. So in current designs, we'll be always looking at flood-proof substations. Through elevations or platform levels, sailing it, to even considering underground and using water pumps to prevent service disruptions caused by extreme weather or even rising sea levels, which we are facing in some countries or coastal cities. So this is a very, very important aspect to think about. How do we safeguard all our power infrastructure assets? Also looking at fire-resistant transmission corridors. A lot of our cables are sometimes buried underground in services tunnels, common services tunnels, and various other locations. So fire resistance considerations are crucial then. Can we put in fire hardened lines, even in wildfire prone regions as well, above ground, in forested areas over long distances? Storm hardening of renewables, including elevating PV installations, wind installations, protected against flooding and typhoons maybe. And also blue-green urban corridors, where we look at nature-based flood management integrated with renewable microstations and resilient uh, green spaces. or in the urban setting as well. So as an example, we completed a work for Singapore's grid operator to look into a few areas. One, flood risk, looking at how do we mitigate flood-prone areas and protect our power infrastructure assets. Two, also look at decarbonization strategy, basically FS6, free replacements. But this aspect requires a lot of interface and integrations with the OEMs. They will have a better control over this possibility. And last but not least, looking at underground usage of power or housing of power infrastructure assets. Next slide. Hybrid systems as well, gaining a lot of momentum. Basically, looking at dual fuel power plants, looking at SMRs, especially in certain nations where renewable energies are challenged. You got to look at other alternatives, and SMR are gaining a lot of momentum, especially in the data center space. Hybrid power plants, where we combine CCGT, conventional CCGTs with renewables and energy storage systems, or even looking at multi-fuel transportation corridors that couple LNG, hydrogen blended together, and so on. So hydrogen-ready CCGT power plants are the way to go. There are huge developments going around the world at the moment on CCGT power plants that are hydrogen-ready, and they are also coupled with battery energy storage systems. So we have been doing a lot of such power plant projects around the world, and with also existing power plants upgrades that coupled with BESS as well. Next slide, please. Now, the last topic that is also very important and very relevant are cybersecurity and data privacy. Cybersecurity risks and challenges are something that cannot be neglected when we talk about power infrastructure resilience. So security, protecting it regulations-wise is not sufficient. We need to then look into measures that can help us monitor, contain any possibility of cyber attack, such as looking at AI-driven grid anomaly detections, air gap SCADA system, as well as continuous penetration testing to keep making sure that the grid infrastructure and systems are well prone and protected and upgraded against any cyber attack or sabotage potential. So this is again also a very important consideration when we look at the overall power system. Next slide, please. So all in all, I've shared a couple of possible potential approaches to looking at power system infrastructure resiliency. And with this, I want to just quickly share a quick last note before we move to the Q&A. Next slide. So more and more does distributed energy resource systems, management systems, as well as hybrid kind of conventional plus renewables plus transmissions, distributions, networks that goes from overhead to barrage to subsea are gaining more and more momentum around the world. And because of this development, we as Savannah Jurong has also been doing a lot of such work around the world. And we have been entrusted to basically develop national grid infrastructures and systems for various countries, including in Australia. And we continue to deliver a lot of cutting-edge, first of its kind developments that are required for us to basically navigate the more and more complex and challenging power systems and grid transmission infrastructure networks. Next. With this, I just want to share a very quick slide on what we believe will be how electrons and green molecules or blue molecules, green and blue electrons will integrate with each other in the long run. This is our visions of a net zero emissions community in the years to come that couples all forms of renewable energy, generation-wise to transmission-wise, and how it interacts with industrial parks, ports, data centers, urban cities, airports to various other infrastructure. And with this, I end my presentation and thank you for your attention.
Thank you, Wee Long. As always, it's now your turn to get involved, so please put forward your questions in the YouTube chat box. A big thank you to everyone who submitted questions whilst registering for this afternoon's webinar. And we might start with some of those, starting with a question we received from Pankaj, who is watching from WA. Good afternoon. Asking you, Wee Long, which renewable energy technologies are preferred and its trend going forward? It could be based on the lowest cost of renewable energy generation, e.g., solar, PV, photovoltaic, or some other factors involved in technology selection. Thank you.
Thank you for the question. But how I'll answer this is there's many ways to answer this, but how I'll answer this is that preferred is actually very subjective when it comes to renewable energy technologies. We got to potentially contextualize this looking at the availability because different countries have different renewable energy resources and the availability is always constrained as well. So we need to look at that as a start. Two, we also then need to look at the total cost of development and ownership. How easily or how expensive technologies plus the context can come together to evoke a cost-effective LCOE at the end of the day. And of course, last but not least, the demand market conditions as well. While you can generate, we also need to look at whether the demand markets requires those kind of electrons at a kind of price. So these are all factors that we need to contextualize first when we look at renewable energy technologies. So as it is, the lowest hanging fruit, in my view, of renewable energy implementation at the moment is still solar energy. So solar energy, the main cause of it is because it is mature and is highly bankable. Of course, there is also potential for wind, especially nearshore wind, onshore wind, nearshore wind, as well as offshore wind are coming to play more and more. And in some other countries, you could potentially even tap onto wave or tidal energy potentials. And of course, hydro is also a very, very important aspect of renewable energy technologies that can come into play. But those renewable energy resources are centered around certain regions. So we then need to contextualize, as I mentioned earlier. So this is what and how I will answer this question at the moment. But one thing to also note is that the cost of, example, solar, battery storage are coming down. With the involvement of such technology, we get better cost returns when we look at that such implementation. But again, all those conditions that I mentioned earlier are still critical when we look at what we mean by being a preferred renewable energy technology.
Thank you for that. Questions come in from Rex. It's a great question, Wheeling, asking you what are the main challenges of the integration of IoT, Internet of Things, and distributed energy systems? Thank you.
I think IoT, as my presentations have addressed, is a very important aspect to think about when you look at grid resiliency in the long run. However, we also need to be cognizant that we are living in a world where conventional grid infrastructure are still in place. We can't just overhaul it overnight to fit an IoT system. So we need to look at compatibility and the integratability of IoT system onto existing grid infrastructure. I believe that is the best way to implement IoT. That is to implement it on top of existing infrastructure rather than basically constructing everything new, which is high capex and very challenging to implement. So when we have to do that, then we then need to then look at how this IoT system can basically couple onto the existing grid infrastructure and allow cost effectiveness and compatibility to happen at the same time. I think that's the biggest challenge in my view.
Thank you, Wheeling. Questions come in from Tate, who is watching in Victoria. Good afternoon to you, Tate. Asking you, Wheeling, how fast will the shift to more smart and renewable energy systems be? And also, how fast is it currently? Thank you.
Again, I contextualize it into not every country or regions are moving at the same pace. A lot of mature economies, especially in EU, maybe in this part of the world, Australia, and so forth, are moving towards adoptions of smart grids and all that. But I think there's also a very cautious approach in terms of how it is implemented. The cautious approach comes into, like what I mentioned earlier, existing grid infrastructure must be able to undertake that. But more and more, you are seeing a lot of pilots, a lot of adoption coming into smaller developments as test case to show how reliable such smart grids can be undertaken as well as integrated into existing grid infrastructure. So I would contextualize it by regions. Now, there are countries that are more adaptable and susceptible to making this happen. But there are also countries where we look at how to then integrate availability and affordability on top of looking at whether it is smart for the time being. The reason is that we should not forget that there are certain parts of the world that is still not able to gain access to even proper electricity supply. So grid infrastructure development is probably can be fundamental in certain regions. But in more mature regions where the grid infrastructure is already quite mature, that's where, or highly urbanized area, that's where we can see more smart grids coming into play. So there's this disparity I would see in adoptions of smart grids around the world.
Thank you. Thank you for that. And staying in Victoria for now, we've had a question from Yosua, who's asking, traditionally distribution networks have been AC. Given distributed energy resources coming into play in distribution networks, what are your thoughts, pros and cons, of distribution networks with DC instead of AC, as DC eliminates reactive powers that are often problematic with DERs? Thanks.
Hmm. A great question, actually. But unfortunately, if you look at our current grid infrastructure, they're all AC, right? And who to blame? You can blame the transformers or you can blame the OEMs who basically invented all this. So when we are now looking at developments of renewable energy sources, new solar farm, wind farms, even storage systems, or even HVDC systems, yeah, they are all DC, right? And yet we still have to convert to suit the system. So unless you microgrid it and then you have something that's decentralized from the grid, then you can look at the potential DC central grid. So this is how I would see the trend going, is that we'll probably still continue with AC moving forward because of, again, the existing grid infrastructure is designed that way. But more and more people are testing DC, so you'll see more decentralized kind of DC grids coming into play, which probably make more sense, more cost efficiency as well. But it will be probably limited to decentralized development at this point.
Thank you. Thank you, Wheeling. Elisa has sent through a great question. Elisa is also watching in Victoria, asking you, what are the considerations particular to renewable energy infrastructure in coastal environments?
Oh, coastal environments, something very close to my heart because everywhere where I reside now in Singapore are coast. So coastal regions, basically, you can have depending on your boundaries as well, you can think about a lot of things. So when you look at, let's say, let's start with solar. What we have a dream about is looking at ocean floating solars. How do we then implement it in the coastal regions? But then when you put solar in the coast or in the sea, it's a totally different consideration than when you put it in the reservoir. And you have to deal with also seawater, which potentially can corrode your system faster than normal. Normal meaning putting in the reservoir. Then you look at wind potential. You can look at the possibility of having wind farms offshore and all that. But of course, again, everything depends on boundaries and where you are. Then you can look at tidal possibilities as well, and wave possibilities if the conditions or sea conditions allows you to do so. So you can harness a lot of possibilities. Then you look at storage. But when you put storage systems near the coast, you got to be extra careful because it is a very highly corrosive environment, which means that the maintainability part of your development needs to be addressed very carefully because the corrosion levels will be higher and faster in those coastal regions. So all in all, these are some of my thought process when we look at coastal developments and what are the key challenges and considerations we need to address. And of course, last but not least, sorry to add one more point, is against sea level rise. When you build such developments near the coast, be wary of sea level rises in time to come.
Thank you for that. Question. It seems following is still the norm nowadays, given that grid forming has been shown to perform better. What are your thoughts on why grid forming has not been widely used? Thank you, Yasso, for that question.
Yeah, thank you, Amanda, for the question. Again, another great question. It's just a trend, right? So grid forming is a new trend. You basically, when you come to grid forming, you basically strengthen the grid system. So you look at the microgrid system, you look at the DIR system, or you even look at potentially a black start resource. Basically, you are able to control. You can host it. At the moment, these are all mainly decentralized in certain generation assets and development. So you can control your output voltage, you can control your frequency. So that basically dictates how the whole system is being played. Why grid forming is still the case? Because we basically any renewable projects, be it a solar farm or wind farm, still have to connect to the grid and play by the rules. So you have transmission codes that governs how you move things and reacts to it. You've got to play by the rules. So it's still entirely dependent on the grid stability, of course, at the end of the day. So grid following is still the way to go, but you see more of grid forming coming to play because of the new trend and the ability of such renewable resources to basically help you decentralize from the grid. So that is what I will see as a trend moving forward. That's towards a grid forming.
Thank you, thank you. We have a question that's come in asking
Mm.
about what measures can you implement to ensure fuel supply diversity and how does it contribute to overall energy infrastructure resilience? Thank you.
Again, a great question. This is a highly important question in the current environment, volatile environment or uncertain environment that we're living in. And in fact, this is not only about diversity. This is a question of energy security. So most locations and most energy systems that we encounter at a national level are working on security. And in security, this leads to diversity. That means looking at multiple sources of energy that we can adapt or adopt. So renewable energy obviously is one because at the very current instance and for a couple of years, decarbonizations of the grid is one of the top priorities of most national agendas. Hence, renewable energy comes first place. The other possibility then now looks into for countries that are very dependent on fossil fuels, including oil and also natural gas, which is still a very dominant clean fuel but most stable, and we often call it as a transitional fuel. We are looking. You could look into the possibility of blending hydrogen into the natural gas, as well as also looking at ammonia or even methanol as potential direct fuel for combustion. You can also move towards even looking at nuclear SMR at this point in time. These are all possibilities of combinations of energy mixes that can help you to increase your energy security. And this diversification also then allows you to ensure that your grid is potentially even stable or prone to any shocks due to energy price changes or energy resource changes around. So you can hedge your bets amongst the different type of resources.
Thank you, Wheeling. We've had a question. A question's come in about hydrogen, very
Hmm.
topical, asking you, how can hydrogen be safely integrated into existing energy systems, including blending with natural gas networks to
Hmm.
enhance energy security? Thank you, Wheeling.
Um, Hydrogen is actually not something new and scary. Let me put it this way. We have been playing with hydrogen for ages because the petrochemical sectors basically produces hydrogen day in, day out. And hydrogen has been flowing through our systems as well, sometimes as town gas in some countries, like in Singapore and even Australia. So we do have already hydrogen blended into natural gas, running as town gas in a lot of our system. I think what we are looking at now is basically in a volume that is slightly different and over probably longer distances, and also potentially using more innovative systems to basically blend it together. But when we blend hydrogens into natural gas, the process is not is very mature, put it that way. But what we need to be cognizant of are the existing infrastructures. Example, if you have a natural gas pipeline already running and you're invested in it, and it is running on a carbon steel, then you need to then look at how hydrogen, when it's implemented in the system, can create more corrosion on some of our system like valves and so on. So this is some of the things that we need to think about when we are designing such processes. Next is then, does that then mean that we need to develop new infrastructure to cater for hydrogen networks? This was again another very testing questions for most energy operators and governments as well. If we were to be able to blend this using existing infrastructure, of course, that is the best. But then the overall ultimate uh, target for most is still to be 100% hydrogen. So you can treat blended hydrogens enriched and natural gas as an intermediate pathway towards the ultimate holy grail of 100% hydrogen network. But at this point in time, I would say it is safe and it is a process that is probably very well known and can be implemented. Of course, all the other conditions must also play a part beyond the technical part as well.
Thank you. Thank you. Questions coming from Franklin. Good afternoon to you, asking, what are the major technical challenges in the transition from fossil fuel generators to renewable energy generators? Thank you.
I think to address this question, the most important aspect is still economics. I think economics is still what is driving a lot of that. Two is basically security. Now, fossil fuel supply chains are mature, and there's a lot of already very secure supply chain to ensure that. Now, I don't believe any economy or any industrialist wants any part of their business to be disrupted. They want consistent flow of electrons coming in that is stable, steady, and that's the only way you can also attract investments, right? So this is still the conventional thought process of how we look at energy resiliency as well as energy security. So that is one. Two, economics, as I earlier mentioned, the cost of basically implementing new energy systems is also a deterrent at this point in time. Take for example, there was a lot of talk about looking at hydrogen systems and then using that as the cleanest fuel to basically go into any combustion generators and so forth. But technology itself have not reached a place whereby we can combust 100% hydrogen, at least at a large scale. So that is again one of the challenge that you also be seeing. Technology improvements needs to come in first, so that our turbines can take on a greater proportion of hydrogen in as a combustion fuel. So that is also the other aspect. And then the third aspect is that new energies also need to be governed. That means there needs to be policies, guidelines, as well as uh, standardizations of policy across the board between countries, so that the supply chain knows how to act, so the importers, the producers, the transporters all knows how to react and comply with. So that standardization is still very important. Just like an example, when we look at hydrogen, first question you will probably always ask, how do you know it's green? Why? How do you know it's produced from green sources and not from other sources or not blue? So the origination again then come into play. How then can we ensure a standardized method to basically originate green hydrogen is something that is in the works. And I think these kind of policies are important for us to ensure that the adoptions of new energy fuels and cleaner fuels can gain greater adoption in time to come.
Thank you for that. And based on the time, we're probably going to have to make this our final question that's come in from Franklin again. Thank you,
Mhm.
Franklin, for your interest in today's webinar. Asking you, Wheeling, a second question is relating to the performance of renewable energy resources compared with traditional generators, especially during fault conditions. Are
Mm.
both on parity?
Well, oh, this is not an easy question to ask. Again, I always like to contextualize this to and not generalize this, because we know solar is intermittent, we know wind is seasonal, and then we know that the reliability and availability in conventional CCGT power plants that uses natural gas, as long as the gas supply do not stop, will continue to run at a high performance level. So all this needs to be dealt with when we look at the overall energy system. So it probably is not fair to compare individually. We should need to compare it from a system perspective. You see, when I combine all these three that I mentioned together and add battery to it, it can be a very reliable overall system. Of course, cost aside, it can be very reliable. So solar and battery can combine together and provide a highly reliable, high load factor system as compared to CCGT. So if we look at all these different systems with all these parity and hybridization coming together, it can be reliable. Then the next question is, how then can we connect them together into existing grids to ensure that this reliability continues to flow. So the base load in the grid system is crucial. We need to continue to ensure that and not allow the intermittency or the seasonality of renewable energy to cause some havoc to it. And that then come into how you design the entire grid system as a whole. So I hope that answer your questions. Uh, I'm not trying to divert the question, but I think we need to be able to contextualize this in that way to make it a fairer comparison. Thank you.
Mm. Thank you. Thank you. Um, what a great session we've had this afternoon, but we have run out of time. And please join me once again in thanking Wee Long Tan for his time and input, and also from presenting from Malaysia this afternoon. I'd also like to thank Engineers Australia's industry partner, SMEC, for their ongoing support. We really would appreciate it if you could take a moment to complete the short feedback form linked in the description box below. Your input helps us to improve and plan for future sessions. Thank you again for joining us today, and I look forward to seeing you at our next Industry Partners event. Thank you and good afternoon.